Hopefully they should be able to hear. I think.
Can you hear me online?
Yes, yes, we can hear you.
Okay. Okay, perfect. Hey, Victor.
Hello.
Hi.
Welcome, virtual Victor.
Yes. Thank you for your office. It's very nice.
You're welcome.
Yeah.
Would you like to get started?
Yep, I'm ready.
Great. So it's my pleasure to introduce you to Jacob. I say Jacob these days. Jacob Kosowski, who's visiting us today, visiting us this week, in fact. He's actually visiting Yara Yapta because he's involved in the survey of chances, if I
It's
understand
the
right.
SPV.
Yeah.
SPV specifically.
Excellent. So Jacob is actually Jacob. I can't stop that. Is a second-year PhD student from the United States and is currently studying at the University of Helsinki. And you moved to Helsinki in 2021, and this was to complete your master's in astronomy. Great. And who are you currently working with at Helsinki?
Alexis Finov, who's also in chances. And
he's an expert on X-ray observations.
Yes, his focus is X-rays, which explains the topic of this talk as well.
Good. So for your research, your interests are galaxy groups and clusters, as your title says, within a local universe, which is why chances.
Exactly, yeah.
And in addition to your thesis work, you're currently working on this SPV, this science verification data of chances project. But outside of astronomy, Jacob has been telling me that you play the cello in your local orchestra.
Yes.
And also is very interested in bird watching. And so he's been having a great time in Chile.
Oh yeah, it's been amazing.
So you said you saw 65 new species of birds?
Yeah.
65.
It was very exciting.
And his favourites, I think so far, were the Humboldt penguins, which are also one of my favourites. And what was the second one?
The Plumbeous rail, which is like a little chicken-like bird that lives in the water.
Apparently very difficult to find outside of Chile. So enjoy your bird life here in Chile, because it's wonderful.
I am.
So correct. So today, Jacob is going to be telling us about using this modified Hausdorff distances to try and find galaxy groups that are identified in both X-rays and optical surveys. So please welcome Jacob.
Thank you very much. Yes, so I've been working. This will talk to be more or less a summary of my first half-ish of my PhD, and specifically focus a lot on the first paper, since that is the foundation for a lot of work that I'll be doing going forward. And a lot of this work is pretty much directly from the paper, in which I collaborated with Alexis, my supervisor, Elmo Temple from Estonia, the University of Porto, and Gary Maun from the University of Astrophysics in Paris, in France. And a lot of the work, especially the optical catalog came from Elmo, which I'll explain later, of course. So yeah, using modified Hausdorff distances to identify X-ray optical galaxy groups is a very loaded title, but hopefully by then you'll understand what all the point of this and why we're bothering to do this. Okay, so yeah. So quick overview of what we'll discuss. So some background and motivation, then I'll discuss the catalogs that I'm using, the X-ray and optical, and also go over the current state and how the identifications are made between these two catalogs and why we need to identify them. Then I'll discuss what the Hausdorff distance even is, because likely no one here has ever heard of it. It's not really an astronomy concept. And then I'll discuss the identifications I made using this MHE with SESS and RASS. summarize those results, talk about what's next. If I have time, I'll go over very preliminary results for the ERES, which is from ERCETA, but we'll see. I have the plots there, but we'll see how it goes. Okay, so what are we talking about here? We are focusing on galaxy groups and clusters, though I believe the majority of the specific things I'm working on are with groups rather than clusters. So these are all gravitationally bound galaxies that can be found pretty much everywhere throughout the universe. They're very common, especially groups. Groups tend to be up to about 50 galaxies, so they're much smaller and more common. Clusters can be hundreds to thousands of galaxies, and then of course you get superclusters, which are clusters of clusters, like Shapley, which is what the SPV work that I'm here doing is focused on. So these clusters and groups, they contain galaxies, they contain hot gas that is ionized, and they contain dark matter. So these three components are pretty much the entire mass of these galaxies. And then, of course, clusters will interact with each other. There will be mergers of clusters. There will be mergers within clusters. And so it's very important to kind of understand the general structure of the larger structure of these clusters and groups so that we can understand their history and perhaps more general history within the universe. So why do X-ray emissions come into play? Well, this gas, this intragalactic gas, this gas permeates the cluster. So this is not specifically bound in any singular galaxy, it's just throughout the entire cluster. And this gets heated up through shock waves from the formation of cluster, from member interactions like collision or just friction type effects. And this heats the gas up to extreme temperatures to the point where it starts emitting in X-rays. So very high energy, but very low luminosity gas. But because of this, these X-rays trace pretty much the entirety of the gas content of these galaxy clusters. So here's not one directly related to my work, but just a nice image where you can see, so these blue dots here show the members of this group specifically. It is Able 2440. And then this color here you can see here is the X-ray emission. And so this is pretty much showing where all the gas is contained within this cluster. And then these are just contours showing significant substructure that could, in this case, could be due to a merger, but that's neither here nor there for this talk. And so the reason why this is so cool is that we can determine almost 100% of the total mass of this cluster by observing the optical galaxies, which is really easy, by observing X-ray gas, which is also pretty easy, and by using dark matter, which is impossible to observe, of course. But we already have two of these options, and cluster mass is relatively easy to calculate using gravitational interactions like shear measurements and things like that. So we can easily get three of the items within this equation, and then we can just calculate for dark matter. So it's obviously simplified, but it's generally fairly straightforward to sort of work backwards to get this big mystery component. And that's why these X-rays are so important. So yeah, so this is going to be the focus of my work is going to be working in both optical and X-ray to get the majority of the baryonic matter within these clusters. So with optical, we can get very good understanding of individual cluster members. We also get good photometric, we have redshifts, spectroscopic and photometric. And of course, spectroscopy is much more accurate, so we get good distances. Both N and X-ray, we get a good understanding of the inter-cluster medium, and also the majority of the baryons within a cluster are X-rays. So very important to have both these components. But the problem is that we cannot really get redshifts from X-rays just by the nature of how we are observing these these the nature of how we observe X-rays. So how do we combine these two? We basically are dealing with a three-dimensional map of optical galaxies because we can get very good redshifts, especially within the local universe. And then we have a 2D map of X-rays. And so it is very common to have a galaxy cluster here and a galaxy cluster here in the same line of sight, completely disconnected from each other, irrelevant. And then you have an X-ray on top of all of that. Who does it belong to? Because it doesn't necessarily have to come from both. It could come from one, it can come from either. It gets even a little more tricky when there's a little offset in the galaxy clusters, because then it's a lot more important to separate them. If it's perfect line of sight, then it might be a combination of the two. But when you have this kind of overlap, it's extremely difficult to determine who is actually emitting the X-ray. And that is why I'm here. So my general thesis is focusing on understanding these warm-hot baryons within these clusters, for focusing on cosmology feedback in general. But I really am trying to find these large-scale emissions of hot baryonic gas within these groups traced by the X-ray emissions. And to do that, I need to figure out where these X-ray emissions are actually coming from, which galaxies groups are coming from, so that I can derive relations between the X-ray luminosity, mass, etc., compared to the optical components. And then eventually I will try to apply this to simulations using the yeah, I lost my word. Using these observations as inputs to simulations to see how they best reproduce different observations within Euclid cosmology specifically. So the optical catalog I'm using is a Friends of Friends group catalog developed by Temple in 2014. What's important about this specifically is that it's volume limited. So here it is the link in length, the distance between individual members is fixed. And so this provides a very good definition of the structure of the galaxy cluster. So we're sacrificing perhaps some completeness for the sake of a very good overall structure of the group, which is what I care more about than make sure we have every single individual galaxy. I've been using two different catalogs, the V180 and V195. It doesn't really matter. I do have it here. So it's basically just the V that is referring to the magnitude limit. So V180 is minus 18 and V195 is up to minus 19 in RMAG. But the more important limitation here is actually in redshift. So the V180 catalog is a much more local catalog. It's not nearly as deep. And so we did this as a way to just test how we can approach how well our system works for very, very close galaxies. And then the V195 is the proper test where we go out to almost 0.9, 0.09. And there we get a very wide range of galaxies to try to match X-ray emissions to. So another thing too is that we personally limited to 0.025 because that better match the X-ray survey we're using. And below this point, it just gets really, really messy as the groups are simply huge on the sky, and it's a little bit more complicated to deal with. And then we also limited to number of galaxies to 10, which makes more sense a little later, but this is basically a statistical solution so that we actually could get decent measurements in our calculations. The X-ray catalog we used for the primary part was the Rosat All-Sky Survey, or RASS, mostly because it is very complete. It covers the SCSS sample completely, and it is also one that my supervisor has worked with a lot. So this wasn't necessarily we do understand that this isn't necessarily the newest survey coming out, but the whole point is that a proof of concept to make sure that we can get this working with contours of X-ray emissions that we knew work well. So we use contours specifically. Again, that will make sense a little in a little bit, but specifically we set to a level of 2 times 10 to the minus 5 counts per second. We tried very different levels, and so this equates to surface brightness of 1.6 times 10 to the minus 12. Basically, we found this as a very good middle ground because we didn't want to lose galaxy groups by increasing our limit of surface brightness. So if we increase surface brightness, things get a bit too broad. Sorry, not too broad, too narrow, and we will naturally start losing pairs with the optical catalogs. And then we lower the surface brightness, things just merge together, sources get confused, it's a big mess. So we found that this was a good middle ground and worked well for our purposes. So how do we do this now? How do we identify these optical groups and X-ray groups together? Well, the main way when you're below 0.2 is the centers. So you take an average of the X-ray emission, you take an average of the position of the galaxy groups, often weighted by mass luminosity. However, this is inherently flawed, but not. It's an open secret that it's a bit flawed because this will inevitably be affected. Of course, especially if we have the weighted averages, this will inevitably be affected by hydrodynamical effects within the cluster, and it's always prone to biasing based on the infalling group members because it will basically toward the more massive group members. And then when you're below 0.2 or above Z0.2, then you can just do direct identification a lot of times, but down at below that level, things start to become a lot more affected by projection, which is another issue we have to deal with for this. And IDing by centers often cannot be taken face value and often has to be validated by simulations to determine if you're actually finding the true center. So there's issues involving for that involving cooling and feedback that has been well studied. So it's basically the best we have at the moment to try to use these centers until today, where there's been actually some good development in modeling cluster outskirts, and galaxy mocks can produce the local galaxy surveys and spectroscopic group selection, quite well. So if we had a method that relied on the overall structure, specifically the outskirts of the clusters, and we were able to find a way to combine that with the X-ray emission, well, that might be a really good approach. So that is what Alexis and I sort of started to devise. And that is where we came to the Hausdorff distance. So this is not, like I said, it's not an astronomical concept from the beginning. It was actually developed in 1993 for machine imaging. So just to identify like early version of facial recognition and object recognition within cameras. So it's basically a way of checking if two contour or two shapes match each other. Now, this is a bit complicated to wrap your head around at first, but it's a very simple concept once you know what it is. So the maximum, largest, minimum distance between two sets, X and Y. So basically, all this means is that if we take this green curve, we take a point on the green curve and we calculate that point's distance to every single point along the blue curve, and we take the minimum of that distance. Then we do it for the next point on the green curve, and so on and so on and so on and so on. And then we take the maximum of all those distances. And then we repeat it from the perspective of the blue. So we take one point, calculate for every distance on the green, take the minimum, and then move on to every single point on the blue, taking the maximum of all of those, and then the maximum of both those values. So it provides a way to determine how well these two objects or two shapes work. Match, yes, thank you. However, the initial version, because it was dealing with maximums, was very prone to drift due to outliers, which is, of course, a very common thing in astronomy. You always have outliers. So actually, only a year later, another computer engineer, the team, modified it to instead use averages. So now this modified version is this is the same. It's just the maximum of the two directions. But now instead of the maximum of the min, basically this is just saying you take the mean of the min. So this helped a lot, of course, with those outliers. And then in 2018, Montes and Julio applied this, as far as I can tell, the first time to astrophysical contours. Specifically, they were comparing the contours like this in ICL, X-rays, and in mass to determine how well each of these trace each other. And it was pretty successful within this application. So we took this concept and have modified it even further because we don't want to compare contours to contours. We want to compare galaxy groups, basically a point cloud, to contours. And so we had to make a little bit of adjustment to get this to work in the way that we preferred it. So we're comparing contours and non-zero pixels of wavelength reconstruction, basically pixels within the contour that contain X-ray emission, and compare that with the actual galaxy cluster points. And basically, the whole reason why we're doing that, and like we're not just doing the contours, is if we compare contours to a galaxy cluster, then inevitably the best kind of match would be galaxies that magically ring around the contour, which is unrealistic. So instead by using the distance to the actual non-zero pixels, a galaxy that's in the center of the cluster, far from the contour, will be very highly weighted as part of the cluster. And so this is turned out to be a very effective way to allow the cluster as a whole to be taken into account. And so we also had to try to minimize the contamination between those optical interlopers, which helped with the non-zero pixels, and then also overlapping X-ray sources, which was a nightmare. And it hasn't fully been solved, but we've kind of just accepted it as a necessary evil of this situation because X-rays are difficult to work with, and X-ray contour, extracting good X-ray contours is also a whole mess. If you talk to Alexis for specifics on that, because I've not delved too deep into actually extracting X-ray contours yet. So we changed, slight change is that we made this a median now instead of an average, again, to minimize contamination. And this gave us control over how many members we actually want to include. So median actually basically is saying that we are taking the best 50% of the group members and contour points as our true members, or like maximal members. So that's why we have 10 galaxies as our minimum. This gives us 5 to work with. The survey does go below 10, but eventually get to the point where we're dealing with trying to match contour against 2 points, and it's not really, there's nothing really there. You can adjust this. We can adjust this percentage, and we did try, but it's a purity versus completeness balance. You increase it to 100%, you're going to get a lot of completeness, a low purity, and vice versa if you decrease it. And 50% is a good middle ground. So that's why we stuck with this. And the other difference that we did is that this is a mean instead of a maximum. And again, this is just a way of clearing out some contamination and outliers, and also takes into account the fact that we are dealing with two difficult to compare quantities, a contour and a point cloud. The beauty too about this, though, is that it doesn't care what you use. We don't need to use X-rays. We don't need to use galaxies. Any contour, any point cloud will work for this. So this is very applicable for other concepts beyond just the stuff I'm working with here. So now we'll just get into some of the actual identifications that were made using this MHC, specifically with SCSS and RASS. Here's a little image of Rosette, just Rosette. And so this is what we get out of our code from just matching. These are showing a histogram of all the different combinations of X-ray and optical group and their respective MHD value. The top one is in arc minutes, so angular units, and then down here we have physical units, megaparsecs, which we calculate by assuming that the match is correct and take the redshift of the galaxy to calculate the actual physical distance between these objects. You'll see in this blue, we have this very nice noise increase. So this will just go off into infinity or until it runs out of galaxies. And then we have here this large overdensity. These are what we're saying are our actual matches. So these are the ones that we actually want to look at to see are they valid. So these are not noise. The separation between red and blue, we set a scaled confusion limit of 5% just to make sure that we aren't assigning more than one contour per galaxy group or vice versa, so that everything is just 1-to-1. And when we do that, we end up with a limit in V195 of about 10 arc minutes or 0.6 megaparsecs, and for V180 about 9 arc minutes and 0.35 megaparsecs, which are, well, this is for V195 specifically. And this value does have to be recalculated for any given sample. It's not a universal value, but within the sample, it seems to work pretty well. Here we just have two examples of what is a match and what's not a match. So this one is 17.4%, so well below this limit. It looks good. This is the red contour. These are the points of the cluster. There's a higher density here. There's some outskirts, but you can see that it looks a good match. Even when it's doing other methods, this could be seen as a good match. And then here, this one is just beyond what we say is a match. Again, contour and points. There are some points that are within the contour. Several of them are not. Maybe there could be another cluster here that is also contributing, but that is not picked up. That is not being plotted here. And that's something we want to test for in the future. But this specific contour against this specific set of points, it is too difficult to say that this is actually a match, and therefore it is deemed not. So this combination is thrown out. This contour might have a match elsewhere. This cluster might have a match elsewhere, but this specific combination is discarded.
So when you say discarded, those points that were inside the contour are discarded as well? Or you
like the points, all the points here are one cluster.
Yeah.
So the pair of this cluster and this contour,
Okay.
that specific combination is deemed, it's not a good match.
Not a match.
But again, the cluster or the contour might have a match that is better, and so that we don't get rid of that contour necessarily. And so this is an overview of the entire sample. The gray points are unmatched, and the blue are the ones that are matched in physical units only, red are angular units only, and green are in both. So it's very clear. You can see that we are making a good sample matching across the entire range of redshift that we're testing. And that's this velocity version on the y-axis. And there's a little bit of difference between if you use megaparsecs, you do get better in the low redshift. If you use degrees, you get better in the higher redshift. But for the most part, it's pretty good just using either. You'll notice there's a lot of points here. That is expected. Here we're running into mainly an issue with the X-rays. They're just not getting deep enough for these small high redshift objects. Things are getting too small. The redshift, the X-ray emissions are too faint, or simply beyond our cutoff for our emissions. But the part that we're really excited about is here, low redshift, low velocity dispersion. We are getting into 50+% completeness in this range, which has not been done before. I think the previous literature said they've gone in like 10%, 15%. So this is a significant improvement in that region. And so here you can see the purity and completeness of the previous plot. So in physical and angular, and you'll see if we look at the low redshift, which is the blue bins, and the low velocity dispersion, which is just on the left here, 60%, 60+% purity at 50% completeness for this low bin, which is very, very exciting for us. And you'll notice though that we do get some weird issues of like 100% completeness at very high purity in the end. That's kind of a statistical error. There's simply, some of these bins are very small and there's simply nothing there. But at least before 500, it's pretty accurate to what we're getting. You also notice that completeness and purity absolutely nosedives in low sigma, higher redshift ranges. And this comes from one, these are very difficult objects to identify in general. There's incomplete sensitivity from RDSS, and when we have incomplete sensitivity, and these are small nearby objects that are way more prone to projection effects, hydrodynamical effects. So it's not unsurprising that as these small objects get further away, they fall below our standards and the matching fails. However, even just bringing up the velocity dispersion by a little bit fixes that issue. So this is extremely localized to small objects rather than across the board. Yeah.
Jacob, can I ask you a question? You impose a condition for your groups to have at least 10 members, right?
Yes. And that could also be affecting this, because these smaller objects could simply have fewer members.
Yeah.
Though that explains the completeness issue. The purity issue is more of the actual size of them in the sky.
But in that sense, the purity issue could be related with overlapping structures that you're forcing to be there because of the 10 number.
Yeah. It is possible. And that might unfortunately be just a limitation of this method, because I mean we have been experimenting, especially with the new data of using less members or using more specific choices in members. And we're working on that. But yeah, so that is definitely contributing to this drop.
So this
Yes.
this is done. How do you know what's a true match in this case?
So basically I repeat this whole process with the real data, and then I create a mock version, and the mock version we use to extract the noise. So it's okay. So yeah. So
There's a mock.
there's a mock.
Yes.
Yeah. And 10 minutes? Yeah, okay. So one other thing that I just want to point out too is that we did not find any strong association between the actual distances or the centers of the X-ray and the optical components and the actual MHD that we measured, implying that the previous method of using only the centers is indeed failing several of these examples. So all of these are matches. The numbers are really small for some reason, but they're all very comfortably deemed as matches. We have ones with the optical centers, X-ray centers outside of the contours. Some of these would be quite close, but then you have examples like this, which are very interesting, because here we have the X-ray center, the optical center, And it looks like this cluster, this little part of the cluster was the only one associated with the X-ray. But even because with that, we still got this as a very, very comfortable match. And so that was very cool to see, as we don't necessarily need all the points in a perfect like blob within the contour. Even partial overlap is enough to determine that this is most likely associated. And also, this whole issue here is not necessarily even one cluster. This might be a result of overmerging within the group catalog, and that has we have been aware of that as a problem. But as an example of testing how this works over smaller contours, over big clusters or big groups in the sky, this was a really nice thing to see, that we didn't need this perfect overlap to get something that was deemed a match. I'm not going to go over all the specifics about this, but basically we tested all of our matches against an X-ray luminosity scaling relation to make sure that what we're getting actually makes sense. They're not purely random, and it works. It aligns very well. The scatter is comparable to previous literature, and this top one is V180, this is V195, so we get more scatter, of course, with V180. And this is due to mass-dependent trends and also different kinds of feedback that affects the luminosity but not the velocity dispersion. So very good to see that what we're getting is actually viable as an output. And then we got similar results for luminosity in X-ray and in the cluster, and as well as checking just as a sanity check against sigma against the luminosity of the cluster as well. So all of that worked really well. So in summary, for this first paper, we were able to get 40 to 50% completeness for low sigma at 65% purity, and going a little even higher, we can get 70, 80% completeness at 300 sigma for 80% purity, which is very exciting and very new. We also, this lack of identification in this low Z bin, this low sigma bin, is very useful for us to see, to understand how we are missing X-ray emissions within this lower range, and how we can fill this gap in some manner. And everything that we found fits the expected scaling relation, so there are no things fall within place. And all of this we sort of wrapped up and published last year. And now we'll be focusing on doing this, but with eROSITA, which is a whole big other challenge with using the eROSITA contours. And this is sort of a next step into making this more applicable for Euclid and for like, it's a proper run now. We did our test run, it works, and now we can move on to the real work. And hopefully use this for hydrodynamic simulation feedback tests. So I think with that, I am basically out of time. So if you're curious, I have a bunch of plots of preliminary results where it works sort of okay, and there's some weird things, but it so far works okay. And so if you have any questions about the eROSITA stuff, come to me after. But thank you very much.
Great. So we're going to start with questions in the room, and then if anybody online wants to write a question, maybe write it now. I'll come to you at the end. So maybe we start with any questions from the students.
Yes.
Very nice talk. I am just wondering about the role of the dynamical state of the clusters in this mismatching between the X-ray centers and the optical the protrusion. Yeah.
This one specifically?
Yeah, for example, that one exactly. Do you know the dynamical state of that cluster? Or?
Well, this cluster specifically is most likely overmerged, which means that this is a cluster and then this is a cluster. So the overmerge within the finding algorithm used to determine what is the cluster and what is not. So the answer is that in this one, there's most likely no dynamical interaction. Well, actually, they're very much, there could be dynamical interaction, but that's not contributing to the centers being solved. And this is more of an example of being able to match using partial parts of the cluster if they're deemed as significant enough. Within clusters like this, where there's a bit of offset, I mean, it could be, there's several different mechanisms. Some of them could just simply be these galaxies are more massive, and that it's sort of where everything's being, the potential is higher here, they're being held here. Some, I think we saw one that was most likely a result of a collision or not collision, but some sort of interaction that moved some of the galaxies without moving much of the X-ray. So there's a few different mechanisms, but yeah, this one specifically is more of a algorithm quirk that was an effort of the code. Yes.
Are you using the Rosita your observations for the same sample of clusters, or are you adding new?
So to start with, we were using the same sample because I can even just show just the overlap here. So the same SDSS sample, because it's a very good SDSS sample. There's not really other volume limited samples of the quality that exist as far as I'm aware. But you'll notice here, there's not much overlap with the current Rosita results, since we only have about half the sky. So we're using maybe a third of the sample, which is causing a lot of problems. These are very messy, these histograms. So there's a lot more noise, and we're dealing with some statistical issues. So I think we should start looking into alternative sources of the optical catalog. But for now, we're testing it just with SDSS because that catalog, in theory, should work. And if we covered the whole sky, it would be good. But we're more dealing with a completeness issue of this coverage for those two. But for the RESS, it was a complete coverage, so we were able to just go for it.
Thank you. Any more questions from the students?
Is it possible to do the match between galaxies, for example, between in X-ray, for example, galaxies that are formed very far away from the cluster center, 5 meter radius, where the galaxy can be preprocessed?
But can you say it again? I'm sorry.
The main question is that we know galaxies of structure, for example, there are a small groups that are formed within the clusters. Also, in the literature, we have evidence that are matched with X-ray emission.
With like the cell groups.
Yeah. So it's possible to match with that as well using X-ray emission. Using this method.
Yeah, I mean, yeah. If you use, I don't think there was anything that would stop you other than just the number of members within those subclusters. Like, if you have enough members, there's no reason why it would stop you. You might have to do it more on like a cluster per cluster basis, just to make sure that you can tune the values to what you want.
So considering the galaxies of structure have less galaxy members and the mass maybe the number of the galaxies in the when you show that for groups with less galaxies, we are probably
yeah, I mean, it comes down to with the number of groups, galaxy members, it comes down to just a numbers issue. If we're using 50%, if you have a galaxy with only 4 members, or subcluster with only 4 members, then you're dealing with 2. Now you could increase that to 100% and use all 4, but then you're going to run into purity issues. So I'm sure there's a way to do it. I'm sure there's definitely a way you could get around it, but it would not be wholesale. Take this and just apply it. You'd have to do some work to get it working for you. But in theory, with enough points, there shouldn't be any reason why you couldn't do it.
which you'd have to raise your X-ray surface density limits. So that-
Yeah, of course. Yeah, you have to definitely use different contours, simply because you need to focus on different parts. But it should be possible. I mean, even I know actually it is possible because this image here was from a test I was doing with just that, where these are these are substructures within this cluster, and I was seeing how I could use NHD to not necessarily identify within small, like see if these galaxies match, but rather identify the members of the cluster that are most likely associated with the substructure. So it's definitely possible, though it's not easy.
Great question. Yeah. Any more questions before? Questions from anybody in the room?
Yeah.
Jacob, I have a couple of questions. The
Yeah.
first one is about the MHD by itself. I wasn't familiar with it.
Oh, like the equation?
Yeah, the way you're applying the MHD, because I wasn't familiar with the methodology and I found it amazing for different stuff, but I was wondering if you think that, for example, could be used for comparing shapes, like itself, for example, how would a sphere will approximate the shape of the cluster, for example, or something like that.
Oh,
Or
yeah.
would it better fit an ellipsis or something with that kind of fashion?
Like spheres in like 3-dimensional
Yes.
specifically? Yeah, yes. Actually, it is used for 3-dimensional matching in non-astronomy things. Like there are 3-dimensional versions of the Hausdorff distance that you could absolutely use. So, I mean, I think if I remember from what I just read, it is pretty much just adding another dimension to like linearly. So it's definitely possible. So you could definitely use it to fit a sphere or an ellipsoid to a cluster to see how well it's matching. Like mathematically, there's no reason why it would not work. That's what the beauty of this method is. Very, very generic. So that would definitely that'd be quite cool to check to use. Yeah, I've seen it used in astronomy context for in that way. So definitely.
I'll ask you later more about that.
Yeah, of course, no problem.
And the other thing that I wanted to ask you was about the center of mass of the X-ray emission. How are you measuring? What are you using from the public catalogs? Because Raul recently published a paper matching the Rosita contours with his filamentary detections, and the first time that he did that, it has some kind of bias towards certain directions between the X-ray and the filamentary detections. And Alexis actually had to like redo the reduction of Rosita to do the match by the end. It's like the astrometry had some kind of bias in some fashion. I don't know exactly what was going on, but I remember that it has like 3 different versions in which the overlap was closer and closer every time. So I don't know if that's something that.
So like there was a situation where there was definitely an association, but the group
Yes,
as
it's
a
like
contour were set far away.
yeah, basically a couple of arguments. I don't remember that.
Yeah.
Well, I have to double check with Alexis to see if he's been taking that into account for the Rosita contour extraction, because he's been dealing. I know there were a lot of problems with that, and I don't remember if he explicitly mentioned that problem. So I'd have to check. But for the actual calculation here, we are not taking, and nothing's weighted to the mass. So that's what we're just focusing on, the general structure of the contour and of the galaxy cluster. So in the pre-processing of extracting the contour, yes, we need to make sure that our contours are indeed accurate to what we're expecting and are unbiased. But I have to double check to see with the Rosita if Alexis took that account. When did Raul figure that out?
Yeah.
Okay. Not recently though. Like this week.
By the end of 2025.
Okay, then he might have actually done that, but I'll confirm with him because that's a good point.
Thank you. Wonderful talk.
Thank you.
One last question for you about the mock comparison.
Yes.
To get the kind of completeness and and the purity.
Yeah.
Obviously, there's probably a few free choices here, right? You've chosen X-ray condor, limit, number of galaxies in a group. I think there's some other stuff like you use the median 50% instead of like 100%. I just wondered, like, had you tried doing it the other way around, see if there's a way to maximize the results using the simulation when you know the right result, deliberately try to maximize by adjusting those parameters in some way.
Well, the mocks are not a mock of the MHE itself. We're actually we make a mock of the galaxy map.
Okay.
So I don't think it would work that way, unfortunately. Yeah. So we're basically scrambling the galaxies while keeping their relative shapes. So yeah, so unfortunately, unfortunately that's not how we're doing the mocks to tune those.
Potentially do that with the hydro simulation. Right?
Yes, and that is something that we want to go to as well once we get to the simulation part of this project.
Yeah. Right. Great. Let me just check and see if there's any. Are there any more questions in the room? And if not, I'll just check if there's any questions online. Chat.
Looks like no.
I think that Flamingo has some icons for with X-rays in case that you want to compare something with something.
I mean, that is what I'm doing.
Great. And I think we can leave it there. Second, take it one more time.
Now we can all eat lunch.
Very nice. Thank you for the good introductions.
Oh yeah, okay. I'm glad to hear that because that was. I mean, it's hard when you know like all this. Like, oh yeah, I know about that, but like, how abstract and attention to someone who doesn't know about that.
I think you're right. I think you started with nice information.
Okay, perfect.
And then there's some technical stuff which you have to follow every step of it.
Yeah, whenever that plot was like the page of the relationship stuff, I was like, why did I add all of this information? It's not really needed. Yeah, exactly. Yeah. I'm like, yeah, I'll explain it all. Thank you. Oh yeah, I mean I have to bring my laptop up anyway as well. So yeah, I'll just meet you in the coffee room in like 5 minutes. See you.
What do you do for lunch? Do you go for lunch with
Yeah, we're just going to the cantina. I think Yara is letting me use her budget for free food. So.
okay. And you go to the main casino.
Yeah, the one that's like downstairs.
Got it.
Yeah. I think tomorrow we're going to go to Ali because I have a celiac disease, so I can't have gluten. So tomorrow it's all gluten in the casino. So I can't eat any of it.
That was nice as well.
Oh yeah, I was there the other day because they also had nothing here, but I just went by myself and it was very tasty. So I look forward to returning.
Well, next, if it happens again, let me know. I'll come with you because I'm happy to go to Ali for lunch.
Well, tomorrow I think we're going. So.
Oh, sounds great. Yeah. Let me.
We usually go around 1, but now, yeah.
Yeah. So we can pack up and go. Let me just check what my crazy timetable is tomorrow. I finish at 1. So perfect.
Oh yeah, perfect.
Or I'll catch you up there.
Sounds good.
Is Alexis still there? Or is he left?
I think everyone left. But he was there. Okay, I wasn't sure if he was gonna make it.
He was.
Yeah. Always stressful when he's on call because like if I
details.
Yeah, exactly. Like if I say like a little detail off that it doesn't really matter for you guys, but he knows it's like, oh no.